Begin.
So we are happy to have today Israel Aumann from the Hebrew University of Jerusalem. Israel is one of the pillars of game theory and he needs no introduction, so I won't give an introduction. And I'll just say one thing is that I was fortunate enough to study in my first year as an undergrad student 2 classes with Israel in set theory and in the introduction of probability class. And those were great classes. And at the end of that year, I decided that mathematics is much more interesting than computer science. And therefore, I'm here now. So thank you very much, Israel, for showing me the light. And now the Zoom room is all yours.
Okay, thank you very much. So let's get started. Let me just recall the abstract, which was the advertisement for this talk. So the backward induction algorithm for perfect information games was formulated well over 100 years ago. It's actually the very beginning of game theory. It's like 10 years before Borel and 20 years before von Neumann. It's or 15 years. Cermello's paper on chess, and that's when it got started, and it sort of sailed along without any trouble until the late 80s and 90s of the last century. Yes. When it suddenly ran aground, okay, people started asking questions. Hey, what is this all about, this backward induction thing? People started asking a lot of questions and gave a lot of different answers, and some said that there is no answer. And okay, so here, as part of the conceptual foundations of backward induction is played a large role the common knowledge of rationality. And specifically, it was shown that in perfect information games, common knowledge of rationality entails the backward induction outcome. Okay, it's a theorem that common knowledge of rationality, if there's common knowledge of rationality, then there is backward induction. Okay, so that was shown. It was also shown that there is no such thing as common knowledge of rationality in perfect information games, and all kinds of beautiful things were shown. And we've almost come to the contradiction in mathematics. Anyway, the result that common knowledge of rationality entails backward induction is not entirely straightforward, to put it mildly, okay? It makes essential use of counterfactual conditionals. What a player would do if one of his notes were reached, even though he knows that it will not be reached. Well, to say the least, that's a concept that's not quite straightforward. And today I want to prove. I think I'm going to prove that common knowledge of rationality entails backward induction in an alternative, entirely straightforward manner. Yeah, it's in fact, it's a little too straightforward for me, and I think there may be a mistake, and maybe some of you will catch it. I don't know, but I at the moment I don't see any mistake, and it uses only the ordinary material conditional of mathematics, which is that if P then Q, okay. Well, P implies Q, let's say, and rather than using the word entail, which means we have a theorem, let's say P implies Q. And the definition of that is that Q or not P. Okay, that's all. That's all. It's a simple statement in the propositional calculus. All right, that's what we're intending to do. Maybe you will trip me up on the way, but I hope not. And let's get started. So first of all, let's define what we're talking about. Backward induction and perfect information games. In a perfect information game like chess, the players move one at a time. That's what it means. So I'm trying to define perfect information here. Each move immediately becomes known to all players. Here we consider only games without chance moves. We're going to keep life simple. And games that terminate after boundedly many moves. Yeah, okay, so we're not, there's a certain finite bound on the moves that you can have. Each play, which is a maximal history in the game, has an outcome. An outcome, okay? Like in chess, there are 3 outcomes, okay? Either black wins or white wins, or it's a draw. 3 outcomes, okay? We have many billions and billions of plays, but we have only 3 outcomes. And each player has a total preference order on the outcomes, okay? So for white, he prefers winning to a draw to losing. Now, black also prefers winning to a draw to losing, but those are different outcomes, okay? The backward induction outcome of a game G, perfect information game, is defined, which we denote BIG, is defined by induction, surprise, on the maximum length n of a play as follows. If n equals 1, okay, if there's just one move, the history, the biggest history has length 1. So in that case, it is the outcome that is best for the unique player, okay? So in other words, the player, his one move is to choose an outcome. We define the backward induction outcome to be the one that is best for him. For general n, the possible actions of the first player I lead to subgames G1, G2, with play length n-1 at most. By the way, you should feel free to interrupt with clarifying questions, okay? Now, well, let's leave the arguments to the end. I'm sure there'll be arguments. With play length n-1 at most. The backward induction outcome of G is that one of the outcomes, BIG1, BIG2, in other words, the backward induction outcomes that I most prefers. Okay, he in fact has to, there are subgames and he must choose the subgame, okay? That's what he does at the move. So let him choose so we define a backward induction by having him choose the outcome that's best for him, okay? So let's, that's a formal definition. Less formally, okay, the backward induction outcome results if the last player to move, I1, makes a choice that's optimal for her. And taking this into account, the previous player, I2, makes a choice that's optimal for her. And taking that into account, the player I3, previous to I2, makes a choice that's optimal for her. And so on, up to and including the opening move.
Okay. So I do have a clarifying question. So how do you handle ties in the definition of backward induction?
Ties? No ties. Okay, there are no ties. Makes a choice that's optimal for her. Okay, she chooses one. In other words, if there are several, no, I'm sorry, I take it back. There are ties. Okay, there are ties. If it's possible to have ties, and she makes a choice that's optimal for her. Okay, and in that case, a choice, not the choice. Okay, she makes any choice that's optimal for her. Okay, and you remember we talk about outcomes. All right, we don't talk about the leaf of the game tree that's reached, the actual play that's played. We talk about outcome. We talk about a backward induction outcome. Okay, so if there are ties, it doesn't matter. You get the same outcome. All right.
But then when there is a tie, and if I choose one of the optimal actions for me, then do all the other players agree on that particular action that I would choose? Is that what you assume?
No. It doesn't matter. They don't have to agree. It doesn't matter because I made an assumption which nobody nobody paid much attention to, but it's a real assumption, and that is that each player has a total preference order on the outcomes. Okay, so there's no such thing. It cannot happen that that the choice between two alternatives for me is a tie. Okay, but the other players care about it. If it's a tie, it leads to the same outcome. Okay, to the same outcome, not to the same leaf of the game tree. Okay,
but for other players,
the same outcome it leads, and the players have a total preference order on the outcomes. All right, so so that takes care of that. Yes.
Just a moment.
So this is not an innocent assumption that each player has a total preference order on the outcomes.
Israel,
thank you.
Okay.
Israel,
Yes.
still there can be more than, if there is more than one backward induction play, there can be more than one backward induction outcome for everybody. So one player, the player at the end has ties, so he can choose one of two actions, but the player who is not playing last can have now two different outcomes.
No, Dubi, when Israel says
I don't
total
think that's
order
correct.
over all outcomes, he means outcomes not just for you, for everyone. Israel assumes that there is no chance where there are two plays where, you know, you could get 7 points either way, so you're tied, but one would cause Israel to get 4 points and the other one would cause Israel to get 3 points.
Exactly.
Order over the product, you know, outcome. If you think.
Understand. So let's look at the last player. Let's say it's player 2. He plays last at some node, and he can have the same outcome. So he can choose either way, right? Left or right.
Yeah, right. You
But
can choose
when
either
he
one.
gets the same
It'll be the same outcome.
Yeah.
It'll be the same outcome,
For
and
him.
the player before that, it's the same outcome.
No, just
for
a
him
moment,
also.
just a moment.
No, Dubi, it's not for him.
Can I finish the question,
everyone.
maybe? Okay, so the last player, like player number 2, can choose between two outcomes between right and left, and he is indifferent because he has the same outcome.
Right.
But player 2, player 1 may have different outcomes.
Yes,
No,
but
No. An outcome is an
player
outcome.
two will have a preference.
Oh, I see. The outcome is not per person.
No, it's not
No,
only
it's an
for all.
outcome like black wins.
Okay,
white
but
wins.
player 2 can have different preferences over outcome.
Yeah, they can have different. Of course.
Okay,
they have
so for
different
him,
preferences.
I see.
Black
Okay.
has different preferences from
Yes,
white.
yes.
Certainly.
Okay, fine. Okay, fine.
Okay.
The outcome.
Okay. So
Professor
I'm just
Aumann-
saying I managed to smuggle that that assumption in, and nobody paid any attention. And but suddenly it becomes important. Yeah. So all right,
Professor Aumann, one interruption. Can I ask quickly one question?
Sure, go ahead. Yeah.
So is it okay to think of an outcome as one path in the game tree?
No, not at all. No. A lot of different plays, in other words, maximal paths in the game tree can have the same outcome. A lot. You know, think of chess. Yes, just 3 outcomes, okay? And you know, almost infinitely many plays. Okay.
But chess players usually care about how they play, whether it's elegant or not.
What, excuse me?
Chess players usually care about how they play, whether they played it elegantly or not.
Yeah, that's right. Okay, no, but you know, I know some chess players. And for chess players, I think they have the right utility functions. They want to win, okay, and they do not want to lose. Yeah, elegant. You know, like Einstein said, elegance is for tailors. But you know, it's nice to have an elegant outcome, but the first thing is you want to win or lose. Yes, you want to win and you don't want to lose. Okay, differently put, if the last player I1 is rational, the previous player I2 knows that the last player is rational, and she herself is rational. So we're going backwards. The last player, okay, and then we're moving upwards in the game tree. And the previous player, I3, knows that the last player and the previous player are irrational, and she herself is rational, and so on, up to and including the opening move, then the BI outcome results, the backward induction outcome results. So a fortiori, all the more so, if all players are rational, all players know that all players are rational, all players know that all players know that all players are rational, all those together, and so on ad infinitum, then we will get the backward induction outcome resulting. Now, this says, this is the definition of common knowledge of rationality. Okay.
Israel, did you define what you mean by rational yet? Before common knowledge even.
Okay, makes a choice that's optimal for making a choice that's optimal. This is less formally, okay? We're going to go back to more formally soon, okay? But at the moment, the title of this slide is less formally, okay? So by rational in this slide, this is going to be the crux of the matter, yes? By rational in this slide, what I mean is doing something that's optimal for you. You're rational if you make an optimal choice, okay? So the conclusion is that common knowledge of rationality entails the backward induction outcome. Now we're going to go back to formally, okay? Not formal, not entirely, but can this insight be made precise, okay? So maybe we should say more precise, okay? The answer is yes. In a representation of a perfect information game as a rooted tree, and I think most of us are familiar with that, a strategy of a player I prescribes an action at each vertex of that player. Each player knows her own strategy and has some knowledge about the strategies of the others, or maybe none at all, or maybe perfect knowledge. Well, in other words, knowledge is the subject that we're going to discuss in the sequel. Knows her own strategy, has some knowledge about the strategies of the others, and has some knowledge about their knowledge. An action A of a player I at a vertex V is irrational if there is an action B at V that I knows is better for her than A. Now, what does that mean exactly? And this is the crux of the matter. She knows that together with the subsequent actions prescribed by the strategy, so she knows something about the strategies, we're not saying what, okay? But if she knows that together with the subsequent actions prescribed by the strategy, action B determines an outcome that she prefers to that determined by A. And then we call A irrational, okay? And now, so if there's another, in other words, if there's something else that she can do with, together with what she knows about the strategies in the sequel, if she knows that she can do better. So an action A is called rational if it is not irrational. That's an action. A strategy of a player is rational if it prescribes rational actions at each vertex of the player, okay? So a player, a strategy prescribes actions. So if it prescribes rational actions at each of its vertices, then he called the strategy rational. Substantive rationality. And we're gonna explain that word substantive on the next slide, but let's just get this definition in. Substantive rationality obtains if the strategies of all players are rational. Okay, call that substantive rationality. All players have rational strategies. Okay, and we'll see afterwards why we call it substantive, or what the meaning of that word is.
Clarification, Israel?
What's that?
Clarification, if I may.
Yeah, please.
Is rationality, it seems, is relative to a strategy. Is that right? It's rational at this strategy. You can say it's rational at a strategy, no? If I read
it's not relative. No. It's not relative to a strategy. It is defined by what you know about the strategies. Okay, it's defined by what you know about the strategies. If you know that if you know that the steak in restaurant B is better than the steak in restaurant A, then it's rational to go to B, not to go to A anyway, right? It's irrational to go to A if you know that they have better food in restaurant B, okay? So if you know that, yeah, it's not relative to the restaurant. If you have some knowledge about the strategies. If you happen to have some knowledge, yeah, we started out, that's what we start out with, okay?
But I have to have knowledge about the chef who cooks the steak.
No, you have to have gone to the restaurant before or heard about, some friends went to the restaurant or something like that. You don't have to have knowledge about the chef. You have to have knowledge about the steak. Okay, okay. So that's rationality. Okay, rationality depends on what you know. Okay, so a rational choice may depend on what you know. Not only may depend, it usually does depend. Okay. Now, a theorem. And this was published in GEB, Ayud.
I remember all the exchange.
Okay. If there is common knowledge of substantive rationality, then the backward induction outcome results. Okay, if you have, that's the theorem. Okay. It was published in in GB, in games and economic behavior. Okay. Now, the proof is by induction on the maximum length of a play. And it's a fairly straightforward proof. There's a lot of, it's not long. It's maybe 2 or 3 pages, you know, at most. 3 pages, I think. There's some, you have to be careful with this stuff. You have to be very, very careful, very careful. It's very tricky. So I'm really afraid that what I'm telling you today is wrong, because I haven't gone through, crossed all the I's and crossed all the T's and dotted all the I's. I haven't done that. It's an idea, but I think the idea is sound. Let's see, okay. Let's go on. So now what's this word substantive? Now, substantive conditionals. A conditional is a statement of the form if P, then Q. And then we have names for P and Q. We call P the antecedent and Q the consequent. In mathematics, this simply means Q or not P, okay? Call such conditionals material. They need not involve any substantive relationship between the antecedent and the consequent. For example, in the material sense, the conditional, if Trump had been re-elected, I would have had eggs for breakfast, is correct. Whether or not I had eggs for breakfast, I mean, Trump was not re-elected, so not P. So, and okay, that's it. And it's Q or not P, that's what it means. In ordinary discourse, the antecedent and the consequent usually do have some substantive relation, okay? Call such conditionals substantive. An example is, if Trump had been re-elected, the Ukrainian crisis would have been averted. This is correct in the material sense because he was not re-elected, like the eggs for breakfast, okay? He was not re-elected, so that makes it true. But arguably, it is not correct in the substantive sense, okay? If people can say, hey, you're talking nonsense, Aumann, yes, even more than usual. The Ukrainian crisis would certainly not have been averted if Trump had been re-elected. It might have come before even, some people would say. I'm not taking a stance on that. I'm just saying that there's some substantive relation between the antecedent and the consequent. Conceptually, the 1995 theorem is based squarely on substantive conditionals. It requires rationality at all vertices, okay, whether they're reached or not, okay? So basically, what you're saying is, if your vertex is reached, then you will move rationally. That is the substance of rationality, okay? But if the vertex is not reached, what does it mean to say that you'll move rationally? Okay. That is, it assumes that if V were reached, even when in fact it is not, the player at V would choose rationally. Okay, then that's a typical substantive conditional. Okay. If we substitute material for substantive conditionals, that is, if we require rationality at reached vertices only, then the theorem becomes false. Okay. Take a look at this game. Okay. It's a very, very simple game. And it plays an important role in the 95 paper. So we have two moves, Anne and Bob, okay? And Anne can move down or across, and then Bob can move down or across, okay? If it is common knowledge that both Anne and Bob go down, then there is common knowledge of rationality at reached vertices in the material sense, okay? Indeed, Bob's vertex is not reached, okay? Is not reached, where they both Anne and Bob go down, so Bob's vertex is not reached. If we only would require material, if we only would require that people are rational at reached vertices, yes, then it's fine, okay? He's not required to choose rationally, and indeed he does not, okay? But he goes down, okay? But Anne's choice is rational, okay? Indeed, by going down, she gets 2, rather than the 1 she would get by going across, because she goes across. And remember how we defined rationality. We defined rationality by following the strategies that we know take place, okay? Now, we assume here that Anne knows that Bob is going to go down. So if you say only that you want the material conditional, if Bob's vertex is reached, then he moves rationally. If you require only that, if in the material sense, so then since his vertex is not reached, the material conditional is satisfied, okay? So that's it. So you do need a substantive conditional. You do need to say, well, Anne looks at the strategy has to be rational, even if it isn't reached, okay? Even if it isn't reached, it has to be rational. That is the substantive part, and that is what leads to the definition and the theorem in that paper. So the outcome is 2-2, which is not the backward induction outcome, okay? The backward induction outcome is 3-3, okay?
Bob, I have a question about Anne, since you invited questions.
Yeah.
So Anne says to herself, if I go straight, Bob will go down.
Yeah.
So
no, she doesn't say that.
So why does
she doesn't say that? You're stealing my my lecture, okay? In accordance with the definition that we had before, okay, let's go back. Here it is, okay? Let's look at this definition. An action A of I at a vertex V is irrational if there is an action B that I knows is better for her than A. Now, what do we mean by that the action is better for her than A? So now we define that, i.e., she knows, okay, that together with the subsequent actions prescribed by the strategies, okay, got that? The subsequent actions prescribed by the strategies, B determines an outcome that she prefers to that determined by A. Now let's go to Bob and Anne. Okay, so now the subsequent strategies, okay, so we have Bob's strategy, okay. Bob's strategy is to go down. That's the subsequent strategy. All right, so together with the subsequent strategies, together with the subsequent strategies, she will be getting 1 if she goes across, together with the subsequent strategy. That's the definition. Okay.
So,
So just a moment.
oh, sorry.
And if she goes down, she'll get 2. So 2 is better than 1. And so if she wants to be rational, she should go down. All right. Now you have raised a great point, and that's my whole lecture. Okay. If we change the definition a little bit and don't consider that substantive rationality that we were talking about before, but we say that if Anne goes straight and she knows that Bob is rational, okay, then he won't do that subsequent strategy. But then okay, making sense of that, making order here is the whole object of this seminar. So let me go ahead. So in other words, what you're saying is right, if I understood you right. If I understood you correctly, you're saying something true, and that is the basis of my talk today. Okay, so together with the definition in the GEB 95 paper, if we cannot substitute material for substantive conditionals. Okay. Okay. And now we have a feeling of discomfort, okay, which we'll spell out. On its face, nothing seems simpler or more straightforward than backward induction. To be sure, backward induction has been challenged as a practical general strategy for playing perfect information games. Okay, and we'll discuss some of that later, maybe this time. But only because at some level in the knowledge hierarchy, some players may impute irrationality to others. Okay, I'm not sure. When all irrationality is ruled out at all levels, backward induction seems intuitively inescapable. Moreover, substantive conditionals do sound like the right conceptual tool to formalize this intuition. As we have seen, rationality means making a choice that leads to an outcome that is preferred to the hypothetical outcomes that would have resulted from other choices. And that's a substantive conditional. And it is this that underlies backward induction. Nevertheless, a feeling of discomfort remains. In the 95 paper, substantive conditionals are extensively discussed as the concept underlying the insight that common knowledge of rationality entails backward induction. Okay, in that paper, more space is given over to verbal discussion of substantive conditionals than to the whole proof. The proof is maybe 2 or 3 pages at most. And the discussion is 5, 6 pages, I don't know what, something like that. But substantive conditionals are not formally defined and so play no role in its formal derivation. The way that substantive conditionals come in to that proof is by demanding that the strategies be rational, even strategies that are not reached, even choices that are made totally off the backward induction path, that are not reached and cannot be reached, that underlies the thing, and that is what we are saying, that if it wasn't in the Ann Bob game, okay, we need to say that Bob, if Ann would move across, then Bob would move across also, okay, if he's rational. But that is, at least on the face of it, it's a substantive conditional, okay? Now, Samet, who's with us today, 1 year later, GB 96, did supply an ingenious formal analysis of hypothetical reasoning, in other words, substantive conditionals leading to backward induction. But it's quite involved, yeah. There's a lot of mathematics in there, yeah. Duby sent it to me yesterday, and I have to admit that I haven't quite finished reading it yet, okay? And I was aware of it at the time, of course, but, you know, time does its damage. For such an apparently basic, simple, straightforward insight as backward induction, could one not devise a relatively simple formulation and proof that rests both formally and conceptually on the ordinary tools of mathematics and logic, including material conditionals, okay? Not substantive conditionals, okay? You know, you could take substantive conditionals with Samet's definition, but maybe we can do something simpler, maybe. So there's a feeling of discomfort here. So could one not devise a relatively simple formulation? And the answer is that yes, one can, as follows. So here's a precise definition, formal, semi-formal definition. A strategy of a player of I is a collection of material conditionals which set forth I's action at each of her vertices V if that vertex V is reached, if material. In other words, either the vertex is not reached or she does what is written, what is prescribed by the strategy. If it's not reached, we don't say anything, nothing. Okay, nothing. Each player knows her own strategy and has some knowledge about the strategies of the other players like before and about their knowledge. Okay.
Can you please apply it to Bob in the game of Ann and Bob?
Well, we'll get there. We'll get to Bob.
I see. Okay, good.
We'll get to Bob. Okay. A vertex V immediately following a vertex U is called U's son. U is called V's father. All right. Now, I apologize for using masculine nouns and pronouns here, but we gave all due honor to the gentler sex. I'm not sure it's allowed to say that. When we call players are female here. So I allowed myself to call vertices male, okay? Without loss of generality, assume that each non-terminal vertex has exactly 2 sons. Okay, if he has more than 2 sons, then split them up, okay, one at a time, okay? So that's not, it's not essential in the math, and it's not, it just makes talking about these things easier. Let V and W be the sons of a reached non-terminal vertex U of player I. Say that W is inferior if I knows that she prefers the outcome if V is reached, okay? She prefers the outcome if V is reached to that if W is reached. Now, I'm going to use the word choosing, but that is a definition. I say that I chooses V rather than W if V is reached and not W, okay? So if V is reached and not W, because there are different suns. So I use the word choosing but the actual thing, whenever you see the word choosing, then you then just substitute if V, if the sun U, if the sun V of U is reached, then I chose V. Okay, it's just a matter of talking. Call I rational at V if at V she does not choose an inferior sun. Call I materially rational if she's rational at all her reached vertices. Say that material rationality obtains if all players are materially rational. Okay? We're talking about specific strategies, yes. So the theorem of today's theorem, if there is common knowledge of material rationality, then the backward induction outcome results. Okay, let's prove that. Well, we won't prove it because like I said, these things are very delicate. Delicate is the right word. And until you have actually written down the formality, I think the formality of this does not go via the easiest way. Anything you can do with syntax, you can do with semantics. Anything you could do with semantics, you could do with syntax. But I think that here the syntax, my feeling is going to be easier. Anyway, let's go back to Anna and Bob.
Can you please go back just one?
Yeah, can I just ask a question about this? So when you say the if V is reached, does she count as knowing this if she knows that she won't choose that direction? So in your original example,
she knows the W has to be inferior. Let's go back to the previous bullet. To say that W is inferior is if I knows that she prefers the outcome if V is reached. Okay, she has to know it.
But when you say if V is reached, if she knows that V is not reached, does she automatically know?
If she knows that V is not reached. In other words, she goes straight on. V, remember, V and W are sons of U. Okay?
I understand,
Bob?
Yeah.
In this first sentence, a strategy of a player is, you don't really mean just a strategy, but you mean a strategy in a given model when you can say whether V is reached or not, because just the strategy doesn't specify which V is reached and which is not. You need to have some knowledge of other strategies, right?
Right.
It's fine.
So it's not a definition of a strategy. It's a definition. I don't know what exactly is the definition of what it is, but just a strategy.
It's a collection of statements, Dubi. It's a collection of statements.
If V is reached,
it's a collection of statements which says that if V is reached, then I will do something specific.
But what does it mean if V is reached? That's which
if
type
V
of
is reached
material.
Either V is reached or V is or nothing.
Okay.
Wait, can I just ask? Can I just ask in one example?
I'm lost.
Can I just ask? Can I just ask in one example? So in your example where Anne could move down or across, and then Bob,
we'll do an analysis of that example. Okay, we'll do an analysis of that example. It's in 2 slides. Okay, so we are going to analyze that very example. okay? So now let V and W be the sons of reached non-time, okay. All right, so we went through this, and the new theorem, which I'm proposing, it's a proposal really, it's a conjecture, one might call it. If there's common knowledge of material rationality, then the backward induction outcome results. Well, now back to Anne and Bob, not 2 slides, but 1 slide.
Yeah.
Okay, here we are with Anne and Bob. Assume common knowledge of material rationality. Note that Anne's vertex is reached because that's the root of the tree. She has the first move. It follows from common knowledge of material rationality, okay, that Anne knows that Bob is materially rational, i.e., he is rational at reached vertices, okay? If she goes across, then Bob's vertex is reached, okay? So Anne knows that Bob will choose across. So
What
she
if
gets
then?
3.
What type of if then you use here? If she goes then, this is material or consequential or what?
Okay, if she goes across, that's either she goes across or she doesn't go across. If she goes across, then the ordinary material is.
But that's not true. If she knows that she goes down because she chooses down, then she will know that she's rational at reached vertices because she knows that she won't reach the second vertex. So it's consistent with CKMR that she goes down.
Right, that she'll get 2, yes, she'll get 2. If she goes down, that is, it's consistent with CKMR, except that it's not consistent for her to go down because she'll get only 2. Well, let's say, let me go continue with this, the full analysis, and then we can discuss it, okay? If she goes across, then Bob's vertex is reached. So if she goes across, then Bob's vertex is reached. So Anne knows that Bob will choose across. So she gets 3, okay? If she goes down, she gets 2. Okay. No, you're right. If she goes down, she gets 2, and there's common knowledge of material rationality, and it's fine, but she gets 2. Yeah, in other words, there's not common knowledge because she is not doing that. She'll get 2 if she goes down, but she'll get 3 if she goes across. So going down is inferior.
Why does she know that if she goes straight, she goes 3?
Because she knows that Bob is materially rational if he is reached. And I'm sorry, that he's rational if he's reached. So if she goes across, then he's reached.
But Bob, I think there is a confusion between material and substantive when you nest one conditional into another. If I say, well, and forget this one, if A, then if B, then C, that's where the confusion arises.
I don't think there's a confusion there, but I'm willing to.
That's exactly what's happening here, am I right?
That's what's going on. Yeah, if she, yeah, I think that we're talking about ordinary material conditionals all the way. You can have you can have nested material conditionals. Why not? Yes.
Okay, but is that okay? I don't know, but that's what I think that's the crux of the problem in this game. It's an if then B.
If
you see?
No. This is not a clarifying question. Okay, this is a discussion.
Oh, I was trying to understand what is being asked.
Let me. This is an argument, and I said myself, I'm not sure this is
confused, that's all.
At all. I'm not sure it's correct, but let me finish the talk, and then we can toss the ball back and forth. Okay. So it follows from common knowledge of material rationality and the fact that Anne's vertex is reached, that Anne does not make an inferior choice at her vertex. Okay, she also has to, okay, so she will not go down. So she chooses a cross, and then Bob chooses a cross. So the backward induction outcome is reached. That's my analysis of this, and I agree with Heracles that this is the crux of the matter. Okay, this is the crux, and if we can make sense out of this, then we're in, and if we can't, then we're out. Okay.
Professor Aumann, one question. Oh.
Yeah, a clarifying question, please, because we're running. Oops, no questions. Okay, finished. How much time do we have, Elon?
So how much time do you need?
I'm going to stop the questions now and maybe 5 minutes or 10 minutes.
Okay, so you have the 5 minutes.
Okay, fine. So the demonstration of the main theorem. So let G be a perfect information game and assume common knowledge of material rationality. We will show by induction on the length n of the longest play that G's outcome, which we call O of G, is equal to the backward induction outcome, BI of G. If n equals 1, there's only one pre-terminal vertex, and it's reached, okay? By common knowledge of material rationality, the player there is rational, so chooses an outcome that's best for her. And that is the BI outcome, BIG. So if n equals 1, there's no problem. For general n, the two possible actions of the first player I, remember we have just 2 sons to each father, of the first player I and G lead to vertices V and W, which define subgames GV and GW with play length n-1 at most. Okay. I knows that in these subgames, common knowledge of material rationality obtains. Okay. By the induction hypothesis, therefore, the outcomes of these subgames are the backward induction outcomes. Okay. If the outcomes are, if the backward induction outcomes are the same, then what that means is that BI of G, there's no difference between the backward induction outcomes of 2 games and the backward induction outcome of the whole game G is also the same outcome. And I chooses V or W, which lead to the same outcome, omega, okay? So omega is also the outcome of G. So that's a trivial case. And now the substantive case is this, but it's also trivial. Otherwise, suppose that BIG, that the subgame GV has a larger backward induction outcome than GW. In that case, the backward induction outcome of G is by definition is G of V. Now, by the induction hypothesis, the outcome of GV, yes, is the backward induction the outcome of GV under the CKMR is equal to the backward induction outcome of GV, and that's bigger than the backward induction outcome of GW, and that is the outcome of GW, and I knows this, okay, because we said that I knows it, okay? So W is inferior, and as the first vertex is reached, okay, we're talking about the first vertex now, then I is, by common knowledge of material rationality, I is rational there, so she chooses V. So the outcome of G under CKMR is equal to the outcome of GV, which is the outcome, which is the backward outcome. So the induction is complete. Okay, that's it's entirely straight. So here I use I like to use a smiley for end of proof rather than these blocks or other things. I tried to introduce a smiley, but the mathematics profession didn't buy it. But here in my lectures, I'm going to use it. Discussion. The demonstration is really extremely simple. Indeed, it just restates the basic logic of backward induction in precise terms. It's hard to understand why it took over a quarter of a century to get there. But there are many very simple insights in the real world which it took many years to see and implement. For example, one-way tolls, okay? Let's say they could have been implemented right at the beginning, but when I was a child, there were no one-way tolls. That shows you how old I am, yes? But there were no one-way tolls on bridges when I was a kid. One queue for many servers, that doesn't exist either when I was a kid. Ski brakes, I don't know if those of you who know skis, yeah, when I started skiing, we had to buckle the skis on with straps, and it always said the straps got mixed up and so on. Now there's a ski brake, no problem, okay? Peruvian railroads, I won't go into that. Nevertheless, a tremendous amount of ink was spilled on this. Common strong belief of rationality, common hypothesis, so much so that I still think that there may well be a mistake, like a lot of you probably think that also. There may well be a mistake waiting for us when we get to the formal proof. Or maybe someone will shoot it down right here and now. Okay. Finally, let me say that.
Sorry, what is a one-way toll, just so I understand the point?
A one-way toll. When I was a kid and you wanted to, you went from Manhattan to New Jersey over the George Washington Bridge and you paid a toll, okay? And then when you went back from New Jersey to Manhattan, you paid a toll, okay? So you had toll booths on both sides, and also in the Lincoln Tunnel, and also in the Holland Tunnel, okay? And the Staten Island Bridge didn't exist yet. Now suddenly somebody had the bright idea to charge a toll only when you're going from New Jersey to Manhattan, in all the bridges, okay? In the Holland Tunnel, the Lincoln Tunnel, the George Washington Bridge, all of them, okay? Now, what are you losing? You charge twice as much, okay? And you save all the toll takers and the toll booths and all that business. Everybody who goes one way, except for a set of measure zero, everybody who goes one way goes the other way also, okay? So that's a one-way toll, okay? And if you want, I can explain ski brakes also. And the Peruvian Railroad also, I can explain that. But finally, let me say this. When I say that common knowledge of material rationality or common knowledge of substantive rationality implies backward induction, I'm not saying that backward induction is a good thing to do. It's rotten, it's terrible, okay? Let me give you an example. I mean, most of you know this, but some of you, maybe there are some younger people around who have not heard of these. Common knowledge of material rationality is a very strong assumption, unlikely to obtain in practice, okay? If it does not obtain, it may well be actually irrational to play backward induction. Consider Nimrod Megiddo's version of Bob Rosenthal's centipede. Oops, here it is, okay? Look at this, okay? Let's do a backward induction on this. Bob obviously will choose down because he doesn't want to get zero. He'll get $1 million, let's say in dollars, okay? He'll get $1 million. So he will choose down. Now, before that, Anne has to move, okay? And she has to choose whether to go down or to go across. Now, if she goes across, she'll get $50,000, okay? And she can get 100,000 if she goes down, so she'll go down. And now it's Bob's, the one before that is Bob, and if he goes down, he'll get 10,000. And if he goes across, since we already decided that Anne is going to get 5,000, if he goes across, if that Anne is going to go down, he'll get just 5,000, okay? And so on and so forth. So so the backward induction outcome of this is for Anne to go down and get $10, okay? That's the backward induction outcome, and it's crazy, right? It's crazy. It's crazy. It's irrational. It's a rational and a rational Bob. They'll stay in for quite a while, but for how long, we don't know, okay? Common knowledge of rationality implies that backward induction calls for Anne to go out at the first move, which is clearly irrational in most practical situations. But by the way, I mean, this is a sort of a footnote, except that on slides you don't have footnotes, okay? When this kind of centipede game was played with chess players, okay? Chess players often do go out immediately. Of course, you can't do an experiment with this kind of sum, okay? You can do experiments only with more reasonable sums. But chess players playing against each other, master chess players, very often they go out immediately. Even though they may be choosing to get $2 when they could have gotten $50. Okay, they go out immediately. So there's an interesting thing there. Yeah, I mean, it sounds crazy, but you know, in the prisoner's dilemma, it also sounds crazy for that the players choose to act to double cross, well, what they call, but. Still, that's the right thing to do. So, so that's it. Thank you very much.
Israel, in the last example, if the terminal was 2020, you would still argue backward?
No, let me argue this, okay? Let me argue this. It's enough for me to argue this. This is, you know, as I said, it's more reasonable when the sums are lower, okay? But
no. If the last two payoffs, the top right, the very top right, were 2020.
We're here, Anne and Bob.
Anne and Bob. If you go all the way to the right, and instead of 00, you have 2020.
Yeah.
Which is more than what she gets if she goes down now. So if she reasons, I don't know when this is.
Wait a minute. Bob is going 2020. Why would Bob, rather than getting $1 million, choose 20? 2020.
I know that.
Bob is making the last move. Bob is making the last move.
No, I see.
Why would Bob, you choose 20 rather than $1 million?
I see the backwards induction, but if you start reasoning for her at the beginning, she's going to get $10, and if she continues, we can, make 515. She can only gain.
If she continues and Bob goes down,
let's make this 15.
And Bob goes down, she gets 5.
make this 15 and the argument, the
Oh, make
backwards
it
argument.
15, then you don't have a centipede anymore. Okay,
think I
the
do.
whole
I
point
think
Bob
I-
Rosenthal's centipede is that
No, I think 15 will still give me a
no,
backwards induction.
you don't have a centipede. You killed the centipede. If you make on the second move, if you make and get 15, then the centipede is dead. This is the centipede. I mean, I gave it a very dramatic sums, but
Yes.
it really depends only on the ordinal. Yeah. In other words, Anne gets a sum, and then if Bob goes down, she gets less, and then she gets more than the original sum on a second move. But on the third move, if Bob goes down, she gets less again. So and so on and so forth. That is the epitome. That is the whole point of the Rosenthal centipede. Rosenthal is no longer with us, by the way. He passed away.
I know.
About when in the 80s he passed away, right?
Yeah, very early.
But Megiddo, thank God, I think is still with us. Yeah.
Megiddo is with us.
Yeah.
But my question is, maybe I can see how to fix this one, but if she's not sure, I mean, this requires, I don't know where, if she was not sure when the exit will occur, but you can argue, maybe you can construct one like that. If you can.
Not sure, and if there's common knowledge, it's up to the players, yes. There's no, it's up to the players. She's really not sure when the exit will occur, okay? So I think if I was Anne, I would go across, absolutely. I would, and I think any reasonable person would go across. And then if I was Bob, I'd still go across, okay? The question is, at what point do you stop that, okay? At the second move, the third move? I don't know, it's not clear. It's not clear at what point. Obviously, I think Bob will go, obviously Bob will go down at his last move, all right?
Yeah.
And therefore Anne will also go down at her last move, right? Because she has only to lose if she goes across. She'll get 50,000 instead of 100,000, and so on. Yeah, it's a nice game. Okay. So that's it. Now there's time for discussion.
Can I ask, like, is this game that different from like a prisoner dilemma with a fixed number of rounds?
Yeah, it is different. It's different because
in spirit.
It's very similar. You're right. It's very similar to a prisoner's dilemma with a fixed number of rounds. But in some sense, it's even starker. First of all, a prisoner's dilemma is not a game of perfect information, and we're talking about games of perfect information today.
The reason why I proposed it is because it shows that you don't need the complexity of repeated prisoner's dilemma in terms of number of strategies. Here it goes very, very slowly, and still you cannot rely on people don't comprehending the complexity of the game. It's very, very simple, and still the backwards induction seems to fail.
Okay, thank you.
Okay, I'll be glad to get comments, and I'm a little encouraged because it didn't get shot down today. Maybe it's gonna survive another day or two, and I'm gonna try to get to work on doing a real formal proof. You'll notice that I called it a demonstration of the new theorem and not a proof, okay? By proof, you have to be really careful in this stuff. Really, really careful. I'm going to try to do this carefully. Thank God I have a lot of stuff to do, so I don't know when I'm going to get to it. So if somebody wants to shoot it down in the meantime, I'll be glad to hear from them. So thank you very, very much. And stay healthy, everybody. Okay.
May I ask a question about what I don't understand in the definition of substantive and material rationality?
Okay, substantive means.
No, basically.
You want to, okay, you want to continue with your question?
Yes, I would like, basically what I see is that it seems that substantive rationality is material when you allow this inductive usage, so that you allow assuming that you are at another point, and then the material rationality, if it's allowed to be used somewhere else, then it becomes substantive. But then it seems to me that the assumption of common knowledge of material rationality should not be allowed to use inductively, because then it simply becomes substantive. So the induction makes it basically substantive. And therefore, it seems to me that material rationality by itself is actually not enough to, it does not imply backward induction. It's like Nash equilibrium, whereas backward induction is kind of like subgame perfection. And for that, you actually need this inductive usage.
Well,
where am I wrong?
I think what you're saying may be right and may be wrong. I don't know, because you're not speaking in precise terms. And
so, can you have an
Yeah, so
example,
okay.
Bob? Can you have an example where you satisfy material rationality, allowing this nesting, but you violate?
I think the and Bob. I think the and Bob thing. I think this is the best that I can do at this point. Here, if we have substantive rationality means that Bob has to choose rationally even when he's not reached.
Right, okay. But Bob, if you allow yourself this nested use of material rationality, is there an example where you satisfy, which differentiates substantive rationality from this nested use of material rationality?
Is a substantive rationality is
here in this example, substantive rationality and material but conditional on something else gives you the same answer.
Yeah, it gives the same answer. You're right. It gives that's a good question.
We want to see a difference between.
It's a good question. It's a good question, and I think I want to look at that.
Okay.
And I do want to look at it, but I think if it's a good question, or if it turns out to be a good question, or in other words, if they're the same, okay? Well, so the conjecture behind that question is that substantive rationality is the same as nested material.
Nested material rationality, yes.
Yeah, right. That is that's fine. That'll be beautiful, because the substantive rationality, okay, is that means that one can, instead of the substantive rationality, one can use this perfectly straightforward, essentially.
Yes, with impunity.
It's straightforward mathematical thing. and instead of this mysterious substantive rationality, mysterious and
it has a formal definition.
Complex. So fine, yeah, I think that'll be great if we can do that. That'll be great. At the moment, I don't have an example. You're right. That's a good way of looking at it. Okay.
I have a question about the proof. Could you go back to the slide with the proof?
Sure. I'd be glad. Here's the proof.
Yeah, so in the third bullet point, you're looking at player I, right?
Yeah.
With two outgoing vertices, with two vertices that can be reached, V and W.
And yeah, two sons, yes.
Yeah, and then you say that, well, if common knowledge of material rationality holds, then I knows that in both of these subgames, GV and GW, common knowledge of material rationality obtains. Now there I have a question, because it seems to me that if you impose common knowledge of material rationality, then I knows that common knowledge of material rationality will only obtain in that subgame that will actually be reached. So that's either GV or GW, but cannot be both, right? Because eventually only GV or GW will be reached.
Yeah, so, okay, good question. Okay, that's fine, that's great. So if GV is reached, then CKMR obtains there. And if GW is reached, then CKMR obtains there, okay? Yeah. So if this is reached, and so now we're saying which one is reached, okay? Which one is reached? So it's up to me. It's up to me to say which one is reached, okay? I've determined this, okay? And in other words, the player I determines it, okay? I determines which one is reached. Whichever one is reached, common knowledge of rationality obtains there, okay? So it's up to me. So do I want V to be reached, or do I want GV to be reached, or do I want GW to be reached? It's up to me.
But that's different from what you're saying here, right? Because you say that I know that in both of these subgames, common knowledge of material rationality obtains.
Good point. Good point. Very good. I think that's a very good point, and I will correct it accordingly, and I can do it right now on the spot. But let me wait till. But that's a good point. Thank you very much. Thank you very much. Instead of saying I knows that in these subgames CKMR obtains, I should have said that I knows that in whichever one of the subgames obtains, in whichever one of V and W are chosen, CKMR obtains. Very good. Wonderful. Thank you very much. That's great. Thank you. Who was the speaker? Andres Pereira. Thank you very much, Andres.
Okay, welcome.
I have also a question, if I may.
Yeah.
I wonder how material it is that you have this total order on the outcomes. I mean, if you have a zero-sum games that's not a problem, but if you're indifferent and you have different outcome pairs for the others, then it's not unique. Do you only need it for the uniqueness? I mean, normally I would say backward induction goes only by your own preferences, which have to be total.
Yeah. I think you are entirely right also. I think this is a very substantive assumption. And on my first slide, I managed to slip it by the audience. It's very substantive, okay? I was so not in the sense of substantive that we've been talking about, but it's an important assumption, and I slipped it by the audience without anybody noticing it, okay? And you're right, that's an important assumption. It's an important assumption, and in fact, as I'm writing this up, yes, I'm far from finished, but in the course of writing it up, I call this outcome genericity.
Oh yeah. Okay.
The assumption of the assumption of genericity that was made in the GB95 paper, full disclosures, I'm the author of that paper. Okay, the assumption that was made there is that at each play, at each terminal vertex, the outcomes are different, and that's far too strong. I mean, it would exclude chess and most other games. So that was called genericity, and that's not a right word. Outcome genericity is this assumption. Okay, this one. Each player has a total preference order on the outcomes. That is outcome genericity. It's excluded to say that if one player has different outcomes, prefers, it's the outcome is the outcome. Yeah, all players have to have different, have to have a total preference, have to actually prefer, not indifferent. If one player is not indifferent between two outcomes, then all players are not indifferent. If one player is indifferent, then all players are indifferent. It's a substantive assumption. It's a genericity assumption, but many games satisfy it. Okay, not all.
Yeah, thank you.
Okay.
Can I ask a question?
Certainly, I'd be delighted.
Can I ask a question?
Yes, please.
Yeah. Wouldn't it be helpful to call this myopic rationality or something in that direction, as to announce that it works out horribly wrong in the centipede game? So it is not rational.
You mean
in
it's not
sense,
because of the centipede?
Yeah, and I think your definition amounts to, let's say, taking into account only one step ahead counterfactuals, rather from reachable nodes. So
no counterfactuals.
Well, one step ahead counterfactuals, because you are going to think about two possible actions of your own. So in a reachable node, you have two possibilities as a player. Yeah. And as the previous question already addressed, one of them is counterfactual by definition. Okay, so in that sense, you only take into account one step ahead counterfactual actions of your own. Is that true? It seems to be the essence of the definition, but also the limitation of it. Because it's wrong, in my opinion, then, at least. As you also said, it is not rational. It is horrible.
In the centipede game.
Yeah, so, but if it's horrible in the centipede game, there is something wrong with the definition as a whole. So it's not rationality.
No.
How can something, or do you mention it as a strong assumption,
let me respond,
but I think it's a wrong assumption.
Let me respond to that. Yeah. I think somewhere I said, I think the common knowledge of rationality is sort of a what it means is that nobody, I said that at some point in the slides, but I forgot where. It means that nobody is imputing irrationality to anybody else at any stage, okay? Nobody thinks that anybody will be irrational at any stage, okay? And not only nobody thinks that, but everybody knows that everybody thinks that, and everybody knows that, and so on and so forth. So in some sense, let me respond to your question, okay? In some sense, we are talking about perfect rationality. There's no irrationality in the system.
No.
Okay, you have to in order to justify any answer to the centipede game, then going out immediately, you have to put some irrationality into the system.
But no.
You have to say that somebody is being irrational at some point, okay?
No.
Or yes.
No.
That is the point.
There is no trace of irrationality walking into this game. Think of the game as having million steps, okay? There is no irrationality whatsoever to walk into the centipede game for the first 90 steps.
But they show me
Nothing.
what should Anne do?
It is a bit like Achilles and the turtle. You have this argument and you can concentrate on it for decades. Yeah. So, well, it's not easy, but I would say it is common knowledge of myopic rationality.
No.
And there is nothing irrational in walking into the centipede game.
No, we're talking about
many people know.
It's not myopic. We're talking about outcomes, okay? We are comparing outcomes, okay? And not just moves, outcomes.
No, but then you have two people confronted with a centipede game, and they know that it's very smart to at least walk until the step 90, okay? And if you know that from each other, you do it, and there you are.
You know what? I think one of my most successful papers is a paper called Agreeing to Disagree.
Yes.
It made a big hit. So let's apply that here, okay? Okay.
I think it's in the 3-step ahead counterfactual that already helps, okay? But it's just a thought.
I think it would help if I would see the person who speaks.
Sorry.
No, where? Who's speaking?
Berend Roda.
Mr. Roda, Dr. Roda, yes.
Sorry.
Well, as I said, let me go back to the definition and show. I'll try to show you why I don't want to call it myopic. Here. Okay. Let V and W be the sons of a reached non-terminal vertex. Okay, say that W is inferior if I knows that she prefers the outcome at the end of the game. Not now, not today or tomorrow. At the end of the game, the outcome, if V is reached, okay? She prefers the outcome if V is reached to that if W is reached.
Yes.
So we're not talking about myopic.
Well, at the start of the centipede game, in fact, you don't know the outcome of continuing the game.
If you don't know, that's what I'm saying. I'm saying, therefore, that common knowledge of rationality, if common knowledge of rationality would obtain in the centipede game, then the players would go out immediately. That's what this theorem says. I mean, or the other theorem, or Summit's theorem, or Battigalli and Siniscalchi's theorem, or
Yeah. But still, it's myopic, in my opinion. So it's not about an incorrect proof, but it's about, let's say, the assumption itself.
All right. So, are there any other questions at this point? Okay, so thank you very much, everybody.
Thank you.
And I'm glad that it wasn't shot down today. Maybe it will be shot down tomorrow. I don't know. Okay, thank you very much.